In this video on our introduction to pipe flow, we're going to talk about how to calculate the volumetric flow rate. So for fully developed laminar flow in an inclined plane, which we previously covered, I want you to recall the scenario on the right-hand side, the diagram on the right-hand side, just to orient you to the equations. I came up with the following equations, 913, 914, and 9.9 for the mean velocities of fully developed laminar flow in an inclined horizontal pipe, and then a generic equation that's good for any incompressible fluid. I want to focus on that equation 9.9. Let's just rearrange that back to get our volumetric flow rate equals our mean velocity times the cross-sectional area of our pipe. So let's clear all this other stuff. Let's just focus on that yellow boxed equation, that volumetric flow rate equation. So if I take that volumetric flow rate equation and I take the mean velocity for an inclined pipe, I just carry that over from the previous slide. And the fact that for a circular pipe, the cross-sectional area is 1/4 times pi times the diameter squared. I just substitute those values in there for the volumetric flow rate. I get the following equations. The volumetric flow rate for an inclined pipe is equal to the pressure difference minus the density times acceleration of gravity times the length times the sine of the alpha, or the inclined angle of the pipe, divided by 128 times the dynamic viscosity times the length times pi times the diameter to the fourth power. And you can see that just by substituting those equations, the mean velocity in the area of cross-section area of a circular pipe, and just doing the algebra, distributing the terms, that's what I get. Now, if I have the more simplified scenario where I have a horizontal pipe, just like we figured out the mean velocities, this sine of alpha goes to 0. And just simplifies the equation down to the volumetric flow rate is equal to the pressure difference from the inlet to the exit, divided by 128 times the dynamic viscosity times the length times pi times d to the fourth. And this is true for both equations, but it's much easier to see in the horizontal pipe. This is where we are able to establish Poiseuille's law. And what that's saying is that for any given pressure drop, for the same pressure drop, P1 and P2, through a pipe of some given length L, the volumetric flow rate is inversely proportional to fluid viscosity, which is down here in the denominator, and proportional to the diameter to the fourth power. So what's your takeaway from that? What does that mean? And I bolded it here in green. It means that if you double the diameter of a pipe with the same pressure inlet and exit and the same fluid for the same set length of pipe, if you simply double the diameter, it increases the volumetric flow rate 16 times. And so that's what Poiseuille's law is saying. And so that, to me, it's kind of mind-blowing. Your gut might say, hey, if I want to increase the volumetric flow rate, I want to double it, I'll just double the diameter of their pipe. And that's not true. If you double the diameter of their pipe, it increases it 16 times, which is pretty neat. Something to consider in your engineering design. That completes this video. If you have any questions, feel free to see your instructor.